Before going to solve some numerical problems in permutations and combinations, let us go through some more basic concepts from combinations. Let us recall the definition of a combination. Out of n given number of things, if r things are chosen in all the possible ways, then each of the ways of selecting is a combination of r things. More precisely, a combination means a team of things has been selected. No question of any preference in the order. No question of any preference in the order. As an example, suppose 1, 2, 3, 4, 5. 5 numbers are there, natural numbers are there. You are supposed to select 4 things. Then they are 1, 2, 3, 4. 1, 2, 3, 5, 1, 3, 4, 5, 2, 3, 4, 5, 1, 2, 4, 5, like that. This is not number 1234. This is a team of 4 numbers. No question of any order here. These are the ways of selecting. How many ways we are able to select? Only 5 ways. And it is of course represented by 5C4 R 5C4 like that. And in general, out of n things, if r things have been chosen, it is denoted by the symbol NCR, and it has been given by, this is equal to n factorial by n minus r factorial into r factorial. More precisely to say, this is nothing but NPR by r factorial. Therefore, NCR is NPR by r factorial, or NPR is therefore equal to NCR into r factorial. And in this last step, we can observe the definition of NPR, the meaning of NPR also. Out of n given things, if r things are to be arranged in all the possible ways, the first thing you have to do is you may have to choose them. After choosing them, you arrange those r things in r places in r factorial. Number of ways of selection is NCR, and number of ways of arranging or those selected r things is r factorial. In total, it is NCR into r factorial. This is about combination. Let us now look at some crucial and important properties about NCR. As we could have just noted, NCR is n factorial by r factorial into n minus r factorial. And let us recall, NC0 is equal to 1 is equal to NCN. NC1 is equal to n is equal to NCN minus 1. NC2 is equal to n into n minus 1 by 2 factorial is equal to NCN minus 2, and so on. If you proceed, NCR is equal to NCN minus R. That is equal to n into n minus 1 into n minus 2 into etc. r factors by r factorial. This is about NCR, and one can easily observe by the definition of NCR itself. NCR is equal to n factorial by r factorial into n minus r factorial. If you can write this r factorial as n minus of n minus r factorial, the same can be understood as NCN minus r. Therefore, NCR is equal to NC n minus r. This is the fundamental concept. Some more things we recollect. NCR minus 1 plus NCR is equal to n plus 1 CR. And another important thing, NCR by NCR minus 1, NCR by n minus 1 CR, NCR by n minus 1 CR minus 1. 3 important ratios. Let us observe them. NCR by NCR minus 1 is n minus of smaller number, that is n minus of r minus 1 by r. And here it is just n by n minus r, and this is simply n by r. These 3 things will of course help us a lot in numerical calculations connecting NCR. So it is very essential, and we are needed to know them and recollect them. Next one, let us now gather some general and famous combinations. Suppose there are some 15 students in a class. We are supposed to form a cricket team of 11. How many members it can be done? Forming a team means just choosing 11 members from those 15 members. It can be done in 15C11 ways. After selecting those 11 members, the various positions in regarding fielding can be arranged, of course, in 11 factorial. That's different. But the way of forming 11 members of the cricket team from 15 members is in C11. And C11. And in general, another example, inclusive of a particular thing, exclusive of a particular thing, they can be understood according to the need of the question, need of the hour. As an example, suppose there are 20 students in a class, 5 persons are to be selected. One person is a recommendation candidate, he is always to be selected. How many ways can you do that? Total number 20. Number to be selected 5. One particular person has already been selected. So still 4 people are to be selected from remaining 19. It can be done 19C4 ways like that. So according to the situation only we think of, it's very easy to understand and reproduce the answer. In a similar way, if a particular person is to be excluded out of those 20 persons, suppose one particular person is not to be selected in the team, then from the remaining 19 persons only, we choose the required 5 persons, that is 19C5 ways. Like this, we choose the number of things. One of the most important and crucial applications of these combinations is about geometry. That is, we are going to deal with geometrical applications of these combinations. Out of them, let us first look at, you please observe the board. Suppose how many points are there? 3, 3, 6, 7. 7 points are there. Out of these 7 points, making use of these 7 points, you can see very well no 3 of them are collinear. No 3 of them are collinear. How many straight line segments you can draw? That is the question before us. To draw a straight line, what are needed? We need 2 points. If you join 2 lines, if you join 2 points, a line will be formed. Therefore, how many straight lines are able to be drawn? To have a straight line, we should have 2 points. Out of 7 points, 2 points can be chosen in how many ways? 7C2 ways. 7C2 straight lines will be obtained. Well, now you observe this diagram. How many points are here? 10 points are here. Out of these 10 points, how many points are collinear? 5 points are collinear. So, using these 10 points, how many straight lines can be obtained? Altogether, taking the total 10 points as a whole, you can draw how many straight lines? 10C2 straight lines. We all know that this is not the correct answer. There are some straight line segments counted extra. What are they? 1 line, 2 lines, 3 lines, 4 lines, 5 lines, 6 lines, like that. These lines must not be counted like that, but of course all these collinear points make 1 line only. Therefore, the required number of straight lines is total straight lines minus how many collinear points are there? 5 collinear points are there. So minus 5C2, all of them are deleted. All of them are deleted, but one particular line joining all those collinear points must be included in the list. Therefore, the total number of straight lines is 10C2 minus 5C2 plus 1. Well, let us now generalize this. There are n points. N points on a plane. Here, 2 cases arise. Number of straight lines that can be formed is first answer NC2 if no 3 of them are collinear. No 3 of them are collinear. and NC2 minus RC2 plus 1 if R points are collinear. If R points are collinear. We could have observed these two answers in the previous discussion. If no question of having any 3 points collinear among the list, the total number of straight line segments is NC2. Whereas, out of n given number of points, if R points are collinear, then the total number of straight lines that can be observed is NC2 minus RC2 plus 1, provided R points are collinear. Just like this, exactly in the similar fashion, if n points are there in a plane, on a plane, number of triangles that can be found by using those n points or vertices is, to have a triangle we must be provided with 3 vertices, isn't it? So, number of triangles means number of ways in which we are supposed to choose 3 points. Hence, the number of triangles is NC3, provided no 3 of them are collinear. If at all some R points are collinear, then NC3 minus RC3, that's all. No question of any plus 1, because collinear points cannot form a triangle. Therefore, the number of triangles making use of those n points, out of which R points are collinear, is NC3 minus RC3. Likewise, number of quadrilaterals NC4, number of pentagons NC5 we are able to have under certain restriction, or according to the data we are supposed to have. One more thing. Observe this diagram. We all know that this is a hexagon. How many vertices are there? 6 vertices are there. How many sides are there? 6 sides are there. How many diagonals will be there in this diagram? To answer this question, we must be knowing the exact and appropriate definition of the word diagonal. What is the diagonal of a polygon? A diagonal of a polygon is just nothing but a straight line joining any 2 vertices different from the sides. You join any 2 vertices, you can be having a line. Of course, if that line is different from the sides, it is a diagonal. Like that, how many diagonals will be there? 1, 2, 3, 4, 5, 6. These are the diagonals. Okay. By understanding the definition of the word diagonal, we could have drawn in the diagram. But how to trace the actual number of diagonals? Suppose there is a polygon having n sides. N sides are there means n vertices will also be there, out of which no 3 of them are collinear. Out of those n vertices, how many straight lines you can draw? NC2 straight lines. They are straight lines joining vertices. Out of all those straight lines, already some n sides are already there. Therefore, NC2 minus n gives you the number of diagonals of a polygon of n sides, and if you can simplify this, n into n minus 1 by 2 minus n, and if you take the LCM as 2, that is n into n minus 3 by 2, you will be having as the number of diagonals. Well, our special interest is the case to deal with a particular polygon at this moment. There is a special polygon in which the number of sides is equal to number of diagonals. What would be that polygon? You guess it? It's very simple. What is he saying? Number of diagonals is equal to number of sides. You equate this formula. N into n minus 3 by 2 is equal to n. Cancel n. N minus 3 is equal to 2 or n is equal to 5. In the last few minutes, we could have recollected a formula to find the number of diagonals of a polygon of n sides. Let us now switch over to another important discussion regarding geometry in which the combinations can be applied. You observe this diagram. All these are parallel lines. How many parallel lines are here? 5 parallel lines. Again observe these. These are also parallel lines. How many parallel lines are here? 6 parallel lines are there. Yes, there has been a question beside this diagram. How many parallelograms can be formed in the network so constructed? That is the question. Let me repeat the question. There is a set of 5 parallel lines. Another set of 6 parallel lines is intersecting the first set, as you see in the diagram. Naturally, so many parallelograms have been constructed in the diagram. In this diagram, how many parallelograms will be there? That is the question. Let us think of. To form a parallelogram, what do you require? 2 lines in this direction, 2 parallel lines in this direction. That is 2 parallel lines in the first set and 2 parallel lines in the second set. How many? These are 5. You can choose 2 in 5C2 ways. These are 6 in number. You can choose in 2 in 6C2 ways. Altogether, the total number of parallelograms that can be constructed in the network so formed in the diagram is 5C2 is 10, 6C2 is 15, 10 into 15 is 150. Before knowing this formula, there are 150 parallelograms. It looks like an unbelievable sentence. No, it is correct. There are 150 parallelograms. There are 150 parallelograms. Let us now generalize this result. Suppose there is a set of m parallel lines and another set of n parallel lines is intersecting the first set. Then the number of parallelograms that can be constructed is MC2 into NC2. MC2 into NC2. That is the number of parallelograms that can be constructed using the 2 sets of parallel lines such that the first set is intersecting the second set. Yes. One more application. Let us observe chessboard first of all. What is a chessboard? Everybody knows it. How many checks are there? 64 checks are there. And that chessboard has been formed by 9 parallel lines horizontal and 9 vertical lines parallel line. 9 vertical parallel lines do comprise a chessboard. You can't believe it. 1, 9 horizontal parallel lines. Altogether, let us believe that it is a chessboard. 9 horizontal parallel lines, 9 vertical parallel lines are there. The question before us is, what is the total number of rectangles that can be formed in a chessboard? To have a rectangle, you must be provided with 2 horizontal parallel lines and 2 vertical parallel lines, so that the total number of rectangles that can be constructed here is 9C2 into 9C2 is equal to, what is 9C2? 36. 9 into 8 by 2 into 1, that is 36 into 36 is 1296. The total number of rectangles of a chessboard is 1296. Well, what is the number of squares that can be formed? That is a beautiful question. How to observe the squares? Like here. At a glance, we observe 64 squares of this size. Yes, 64. Out of these 64 squares, which are congruent, let me take each side of these as 1 unit. So we have squares of each side 1 unit, squares of each side 2 units, squares of each side 3 units, and so on, squares of side 8 units you have. They must be collected. Let us start from the beginning. How many squares in which each side is 8 units will be there? There is only one, the entire chessboard. How many squares in which each side is of 7 units? How many? 7 means like this or like this. Again, in the horizontal manner, like this or like this. This can be chosen in 2 ways. This can be chosen in 2 ways. That is 2 into 2, 2 square. So number of sides of number of squares in which each side is of 8 units is 1. 7 units is 2 square. 6 units is 3 square. Like that, if you proceed, the total number of squares can be imagined, rather estimated as 1 square plus 2 square plus etc. 8 square by using the formula n into n plus 1 into 2n plus 1 by 6, that is 8 into 17 plus 1, 17 into 9 by 2, that is by 6, it is of course 204. What is the total number of squares? 204. What is the total number of rectangles? 12 and 6. There has been a good formula and problems also in probability regarding these two concepts. This is the way in which we estimate the number of squares and number of rectangles on a chessboard. Now we discuss with different types of divisions. Suppose I have 10 things with me. I like to distribute those 10 things between 2 persons before me. 7 things to the first person and 3 things to the second person. How many ways? 10 things are there with me. First I choose 7 things to give to the first person, and remaining 3 are there. Those 3 I give to the second person. What is the number of ways? 10 is 7, that is 10 factorial by 7 factorial into 10 minus 7, 3 factorial. Observe here, 10 things are there. They have been distributed between 2 persons to contain 7 and 3 things. Now you suppose 15 things are with me. Out of these 15 things, I am supposed to give 8 things to the first person, 4 things to the second person, and 3 things to the third person. In how many ways? There are 2 types of work. One thing is the number of things that must be given to the first person, 8. 15 see 8 ways. Now I have 7 things with me. Out of those 7 things, I am supposed to give 4 things to the second person. Now I have only 3 things with me. Those 3 things will be given to the third person. You observe this. What is 15C8? 15 factorial by 8 factorial into 15 minus 8 is 7 factorial. 7C4 is 7 factorial by 4 factorial into 7 minus 4 is 3 factorial. Cancelling this 7 factorial, you are going to observe this answer to be 8 factorial into 4 factorial into 3 factorial. 15 things, distribution must be done among 3 persons to contain 8, 4 and 3 respectively. It could be done in 15 factorial by 8 factorial into 4 factorial into 3 factorial. Very simple, straight and direct concept here. Let us now generalize this. P plus Q plus R things are to be divided into 3 groups to contain P things, Q things and R things respectively. What is the number of ways? You just imagine this procedure. This could be done in P plus Q plus R factorial by P factorial into Q factorial into R factorial into R factorial. Well, let us now observe some numerical examples here. I think everybody believes that there are 52 cards in the set of playing cards. Those 52 cards must be distributed into 4 groups to contain 20, 10, 8, 4 cards respectively. How many ways can we distribute them? 52 factorial by 20 factorial into 10 factorial into 8 factorial into 4 factorial. That's all. Now the question arises. 52 cards are to be distributed. They are to be divided into 4 equal groups. How many ways? 4 equal groups. 52 factorial by 52 cards are there. 4 groups are to be formed. Each group should contain 13 cards. So 52 factorial by 13 factorial into 13 factorial into 13 factorial into 13 factorial. That is 13 factorial whole power 4. That's all. This is the way in which an ordinary boy can estimate. You see, there is a mysterious object here. Let us observe it carefully. 52 cards are to be made into 4 equal groups. 52 cards are to be made into 4 equal groups. This is one question. You observe the another question. 52 cards to be made into 4 equal groups, and 52 cards are to be distributed among 4 hands equally. Is there any difference? There is a thin difference, little difference. Here, in the first question, we are supposed to make them 4 groups only. No question of any order among the groups. But here, there has been an order. There are 52 cards. They are to be made into 4 groups. The first group of 13 cards to be given the first hand, next second hand, next third hand, next fourth hand. Order of the groups is fixed here, but it is not done here. With this difference to observe, what is the fate of the answer? Here, the answer will be 52 factorial by 13 factorial into 13 factorial into 13 factorial into 13 factorial, that is whole power 4 into 4 factorial extra, because those 4 equal groups can be rearranged among themselves. Again, that so-called 4 factorial does not appear here. This is 13 factorial whole power 4 only. It is so easy, so important, so dangerous if you do not observe. With a little difference, we are able to have 2 types of answers. Here, no question of any order of the groups present. Here, order of the groups has been fixed here. If it is fixed, the answer will be 52 factorial by 13 factorial whole power 4 only. If it is not fixed, then it is 52 factorial by 13 factorial whole power 4 into 4 factorial.